Hello and welcome to Earth Science Online. Today we're going to be talking about rocks. But before we begin our discussion on rocks, let's look at our warm-up question. Our warm-up question is actually the critical thinking question from our last lesson on minerals. And those are three parts to this question. First, explain why color is not a good test for distinguishing between pyrite and gold. What test is most reliable for identifying these two minerals? Second component, compare and contrast cleavage and fracture. Give an example of a mineral with cleavage and a mineral with fracture. Third component, what is the hardness of a mineral if it scratches a penny but will not scratch glass? So take a few moments to look at your answers to your critical thinking question in the back of your packet from minerals. And then I will go over the answers now. So the first component, explain why color is not a good test for distinguishing between pyrite and gold. What test is most reliable for identifying these two minerals? The minerals are similar in color, so that's why color would not be a good test. The best test to distinguish between pyrite and gold is the streak test because they're going to have a different streak. You remember we talked about in our last lesson that the mineral pyrite is fool's gold because it's golden color. But its streak is always going to be kind of a dark blackish gray. Compare and contrast cleavage and fracture. Give an example of a mineral with cleavage and a mineral with fracture. So cleavage and fracture describe how minerals split. You remember we talked about this being a test for identification of minerals. So minerals with cleavage split relatively easily and evenly break along one or more planes. A good example would be mica. Minerals with fracture break unevenly along rough, jagged edges, and an example of that would be quartz. What is the hardness of a mineral if it scratches a penny but will not scratch glass? So if you looked at your Mohs hardness scale from our last lesson, you saw that a penny has a hardness of about 3.5. A piece of glass has a hardness of about 5.5. So a mineral that would scratch a penny but not glass has a hardness greater than 3.5 but less than 5.5. And you remember we talked about last time the fact that when testing for hardness, a lot of times it's going to be a range between two of those known minerals out of the 10. So let's talk about rocks. So we know rocks are made up of minerals. And what I have in front of you is the rock cycle. So you can see here, there's a lot going on in the rock cycle. So it is cyclical. You see here with magma, the cooling of magma causes it to crystallize and form igneous rock. But then igneous rock in return can melt and form back into magma. Metamorphic rock, if it melts, it also can go back to being magma. Metamorphic rock, though, comes from sedimentary rock when it has heat and pressure added to it. That's how you get metamorphic rock. Weathering and erosion of metamorphic rock creates sediment. So metamorphic rock can either melt and become magma or can weather and erode and become sediment. Sedimentary rock, same way. It can weather and erode to become sediment, or it can compact and cement together to become sedimentary rock. And then igneous rock can also become sediment by weathering and erosion. So a lot going on here, and we'll talk about the components of the rock cycle. And this should all come together and be clear by the end of the lesson. So let's begin with igneous rock. So rocks are made of two or more minerals. So that's the difference between minerals and rocks. Rocks are made of minerals. Minerals are made of elements in the periodic table. So you can say that in a way, rocks and minerals are made of the same thing, but in a different capacity. Because what you're going to have is minerals are made up of one or more elements in the periodic table. And so then you have a mineral that's made up of, say, let's say you have one mineral that's made up of one element and one mineral that's made up of two elements, and it comes together, and those two minerals come together and they're going to form a rock. So you see how rocks are a little bit more complex than minerals because we have more components going on there. Now, there are three types of rocks: igneous, sedimentary, and metamorphic. So let's take a look at igneous first. So igneous rock. Igneous rocks form from the crystallization of magma. Magma, as we've talked about before, is the molted or melted rock beneath Earth's surface. Lava is magma that flows out onto Earth's surface. So once magma is out onto Earth's surface, we no longer call it magma, we call it lava. Classification is based on mineral composition. So what minerals that are making up igneous rocks, that's going to determine how the igneous rock is classified. Igneous rocks are also known for being strong and durable. So there's two different kinds of igneous rocks that you find: extrusive and intrusive. So extrusive igneous rocks are fine-grained igneous rocks. They cool quickly on Earth's surface. And remember, we talked about rocks that cool quickly from magma generally don't have easily recognized crystal structure patterns. And you can see here, we're looking at obsidian. It's cooled quickly, and we don't really see the structure very well. We can't really distinguish that just with our eyes. We would have to take a microscope and really look at that more closely. So extrusive rocks are going to be Earth's surface. So think of extrusive, X as out of the inner part of Earth. So crust, Earth's surface. Intrusive, on the other hand, are going to be beneath Earth's surface. So think of in Earth. They are coarse-grained. They cool slowly beneath Earth's surface. And you can see here, if you look at this rock, you can kind of see we have a little bit of a hexagonal pattern. If you look at that, you can see that readily with your eye. But then if you move closer in, you could see it a little better with a microscope, but you can see it pretty readily. It's cooled slowly, so that's given the crystals time to come together, given all those elements time to form. Those atoms form molecules. Those molecules can come together and form those repeating over and over patterns, and so that's going to create a nice crystal structure that we can readily see. Okay. So let's talk about magma for a minute. So we know where igneous rock comes from. So let's talk about it. All right, so magma. There are three types of magma. So mineral content impacts how magma is formed because different minerals have different melting points. So oceanic crust, for example, is rich in iron and magnesium. It melts at higher temperatures than continental crust, which contains higher levels of silicon and aluminum. So that melting point is going to determine which minerals actually come together and form that crystal structure. Because if it's not going to melt at whatever degrees that is, if one mineral, if one element doesn't melt at a certain degree Celsius, and another does, then that other is what's going to melt and come together with other elements to form the mineral. So if you see here, your three types of magma, you have rhyolitic. It has 70% silica content, andesitic, 60% silica content, and basaltic has 50% silica content. So you notice that the continental crust is going to melt at lower temperatures, and it has more silicon and aluminum. So you can see here, if you look at silica, your silica content, your rhyolitic and andesitic are going to be continental crust, whereas your basaltic is going to be that oceanic crust. So melting factors. So temperature, rocks melt at very high temperatures, and the deeper you go beneath the Earth's surface, the hotter it gets. Another factor besides temperature is depth. More depth, more pressure. So the more pressure that is being put on these elements that are forming molecules, the more they're going to come together. Pressure, more pressure equals higher melting point. So the deeper you go, the more pressure you're going to have. The more pressure you have, the higher melting point you're going to have. So if you have more pressure that is pushing on these elements, it's going to take a higher melting point to get these rocks to melt. And then water content. If they have more water in them, it's a lower melting point. It doesn't take as long to melt. So rocks melt only under the right combination of factors. And there's something that we call partial melting. And that is minerals melting at lower temperatures than others. It results in kind of a slushy mixture. So if you had ice cubes, and in the ice cubes you had wax from crayons, and you put them in a pan on a burner on a stove, the ice would of course melt faster than the wax from the crayons. The wax would melt a little bit, but the ice would melt pretty quickly. So the remains of the crayon, so let's say we melted them for so many minutes and all of the ice had melted, but not all the wax had completely melted. This would represent partial melting. So what happens is the water melts away, and then those elements remaining are what is left from the partial melting. Okay, so how do they crystallize? So when magma cools, it crystallizes or hardens in the reverse order of how it melted. So whatever the last element to melt, that's the first to harden. So like in our crayon and wax, our wax and ice demonstration that we talked about, the wax would actually come together and cool first. So that would be the order that it would cool and crystallize in. You'd have the wax first, and then you'd have the water next. Magma is made up of different minerals. So during the crystallization process, some minerals become solid while others remain molten. So that's something else to note. Just as they have different melting points, they have different points that they solidify. So remaking rocks at different temperatures is called fractional crystallization, and that's the opposite of partial melting. So you see here we have weathering, and then we have, okay, they get transported and deposed into sediments, and then lithification happens, and we have sedimentary rocks here. Okay, then as they go deeper beneath the surface and more pressure is applied, we get metamorphism, and that turns into metamorphic rocks. So then it's getting hotter and hotter, pressure is more and more, so those metamorphic rocks melt, and they turn into magma. And then the elements within those metamorphic rocks are going to crystallize. And it varies with what elements come together. It usually, if they have the same melting points and the same solidification points, those are going to be elements that come together. So they're going to come together, and then the ones that stay beneath the surface are igneous rocks that are intrusive. The ones that consolidate and come out of the surface are going to be extrusive. And those that stay beneath the surface, uplift and exposure over time can cause some of those igneous rocks to come up. The extrusive rocks, they come up from weathering, and they also can go back and form through metamorphism. They can form metamorphic rock. So those igneous rocks that are extrusive, if they get back down into the earth and back down into the higher pressures and higher temperatures, they can become metamorphic. So It's all a cycle. So Bowen's reaction series. So what is this? It was created in the early 1900s by a Canadian geologist. His name was N.L. Bowen. It gives a predictable pattern between cooling magma and mineral formation. So Bowen actually discovered two main patterns or branches of crystallization. So the first pattern is characterized by a continuous gradual change in the feldspar group. So we talked about feldspar as a mineral. So they're pretty reliable and pretty predictable in how they're going to behave. The second pattern is characterized by an abrupt change of mineral type in the iron magnesium group. So they're always going to behave in kind of a similar way, and it's going to be in a more abrupt change rather than a gradual change. So let's take a look at how that works. So, okay, over here you have your feldspars over here to the right. So you see here, these are your feldspars, and they start out being calcium rich. And what happens is when magma, as the magma cools, the first feldspars are calcium rich, and then as the cooling continues, the feldspars begin reacting with the magma. And so the elements within the feldspars and whatever elements are in the magma are going to come together, and that's going to make them more sodium rich by the time they get lower in our surface. And it's a gradual change over time. And you can see here, this is the different types of igneous rocks that you see as you go down further beneath Earth's crust. You start with that's supposed to say ultramorphic, actually. And they give you examples of comatolite and peridotite, basaltic, basalt and gabbro, andesitic, andesite and diorite, and then granitic, rhyolite, and granite. So these types of igneous rock are seen as you go down beneath the surface, and these up here are going to be more calcium rich, while these here are going to be more sodium rich. Okay, and then let's take a look over here to the left, the iron rich minerals. So they undergo abrupt changes. So when magma rich in iron, like olivine, for example, cools to 1800 degrees Celsius, it begins to crystallize and continues to form until the temperature drops to 1557 Celsius. And at that temperature, a completely new mineral called pyroxene begins to form. So what happens is you've got these high temperatures, and you have olivine crystallizing, and then as it reacts with the magma and we get to the higher temperatures, we get to those new melting points, and so new elements now can melt and can come together, and so that's why these new minerals can continually form. And so what happens is you just have these abrupt changes. They just become brand new minerals. So you start with olivine, olivine, and then you have pyroxene, amphibole, biotite mica, potassium feldspar, muscovite mica, and finally quartz. So it's all gonna go down and change as the pressure and the heat change. So that is Bowen's reaction series. Get these eraser marks, these markings from the annotation erased. We can go on to our next topic. Okay. So going back to igneous rocks. So minerals form distinct bands or layers. So once the crystallization process happens and it begins cooling, we see these bands forming. They can be valuable sources of rare minerals. Igneous rocks, we talked about being broadly classified as extrusive or intrusive, but they can also be classified furthermore. So mineral composition and physical properties, such as the texture and the grain size, are going to help determine what type of igneous rock it is. The three main groups of igneous rocks include felsic, mafic, and intermediate. So let's talk about those groups for a minute. So classification of igneous rocks. So color, the felsic group are going to be your light colored igneous rocks. They're going to have a high silica content, and they are going to contain quartz. Intermediate, that's going to be a mix between those two, between mafic and felsic. Mafic is going to be dark, and it's going to have a lower silica content, and it's going to contain iron and magnesium. So intermediate is going to be somewhere in between the light and dark color. It's going to be kind of an intermediate color. As far as silica content goes, it's just going to have a medium content. And then as far as the elements making it up, it's going to have a mixture of some of the elements that make up quartz and some of the elements that make up iron and magnesium. Then we have ultramafic. Ultramafic is darker. It's going to have a lower silica content. It's going to have more iron and more magnesium. It's also going to have more plagioclase, biotite, amphibole, pyroxene, and olivine. So as you go deeper down Earth's surface, you're gonna find more of these elements here, as I showed you on Bowen's reaction series. So grain size. Grain size is, of course, the size of the visible crystals. We talked about that before. Obsidian having a very fine grain, for example, and granite having a very large grain, for example. So that is an identifier for us. And then veins. So igneous rocks have veins. What I mean by veins is they're formed at the end of crystallization. So you have this fluid that's left over. It contains lots of silica and other leftover elements that didn't form common minerals. You can have things like gold, lead, copper, and silver. So fluid fills the gaps and the crevices, and then quartz plus whatever that element that's left over reforms and hardens as rock. So that's where the veins come in with igneous rocks. And then special veins. Veins of coarse, large grained rocks are called pegmatites. So you can see here, they're bigger, and they can be a good source of some trace elements because they are larger. And then finally, diamonds. Let's talk about diamonds for a minute. They're formed in a rare rock called kimberlite. And most mined diamonds are used in cutting and grinding and polishing tools. Why? Because nothing is harder than a diamond. So diamonds are actually used to cut other diamonds and can be used to cut other gemstones as well. Okay, so let's talk about sediment for a minute. So what is sediment? All right, so sediments are pieces of solid material deposited on Earth's surface by wind or water or ice or gravity or chemical precipitation. Over time, they break down into smaller pieces, and these pieces are called clastic sediments. They can be big boulders or microscopic fragments. Erosion. We've talked about erosion before in class. It's the removal and movement of surface materials from one place to another, and eroded materials are always almost carried downhill every time. So, let's see, went the wrong way. All right, so here's erosion. Here are some natural factors: wind strength and direction, rain, angle, slope, frost action. You can see just all these different ways that we can have erosion. So most sediments are deposited in depressions called sedimentary basins, and these can be up to 8 kilometers thick, so pretty thick. The bottom layers of these basins have higher pressure and temperature, which makes sense because we talked about as you go beneath Earth's surface, the temperature and pressure gets higher. These conditions cause what's called lithification, the physical and chemical processes that transform sediments into sedimentary rocks. So cementation. Cementation occurs when mineral growth bonds sediment grains together into solid rock. Okay, so a good example is a Rice Krispie treat. So I'm going to show you. So I have a Rice Krispie treat with me. All right, so if you look at a Rice Krispie treat and you look at the marshmallow, the gooey marshmallow inside, you can see that that gooey marshmallow would be the new that's forming, that new that's crystallizing and forming there, and those older grains are going to be represented by the Krispies. So what's going to happen is you're going to have your gooey marshmallow is going to be your new sediment coming in and cementing all of this together, and these other larger grains are going to be your old that were already there. So that's how that works with sedimentary rock. I don't think sedimentary rocks taste as good as Rice Krispie treats, though. So the new mineral forming between those bonding existing grains, that's the marshmallow, and then those existing grains are going to be what's already there. Okay. So now let's talk about sedimentary rock. All right, so we know the weathering and erosion of sedimentary rock makes it sediment. We know that compaction and cementation, like a Rice Krispie treat, makes it into actual sedimentary rock. So what are some properties? Okay, so there are three types: clastic, organic, and chemical. So clastic are going to be your coarse grain, medium grain, and fine grain. The rock name conglomerate or breccia, sandstone or shale. Methods of formation are going to be lithification and clastic sediments. Here we have our chemicals. So sedimentary rocks that are formed by chemicals. Some examples are calcite and halite and gypsum. The rock names are limestone, rock salt, rock gypsum. And the way they form is the precipitation of dissolved minerals from water. So basically what's going to happen is you have these dissolved minerals, and now that solute to solvent balance has been disrupted, and so now you have more of your solute, and it's going to come together and going to create minerals. Organic, calcium carbonate shells. So rocks can be organic, minerals cannot. So that's another thing to notice. Limestone, coal, so accumulation of lithification of remains of living things. So inside of shells or plant matter, you can have minerals that accumulate inside, and they interact with things in that living, from that living system. So that's how you can have organic sedimentary rocks. So clastic rocks, let's talk about them first. So clastic rocks are coarse grain. They consist of gravel-sized rock and mineral fragments. Conglomerates are sedimentary rocks with coarse grain rounded particles, and breccia contains more angular particles. Formation. So gravel is transported by high energy flows of water. So rivers, ocean waves, glacial melting. Those high energy flows of water are going to transport all that gravel. Long distance transport allows for the grains to become more rounded, which would make sense that there's going to be kind of a polishing element to it. Short distance transport results in angular grains. So you can kind of know if it's been a long distance or a short distance transport sedimentary rock by looking at the grains. They're known for bedding, visible horizontal layering. Graded bedding as particle size becomes coarser and heavier towards the bottom layers. So if you look here, this is a picture of the Grand Canyon on the left side. I had the privilege of visiting the Grand Canyon a couple of summers ago, and it really does look this way. You do have these banded layers, and they do become coarser and heavier as you go towards the bottom. So if you're hiking down, you can see that. Cross-bedding. Cross-bedding forms as inclined layers of sediment move forward across a horizontal surface. So you can see here, you have, this is kind of going in sort of a kind of a sideways direction, but then these are a little bit more of a horizontal up and down. So you can see how as they're moving, as these layers are moving forward across this horizontal surface, as they move forward, as they go along the surface, it can change. So the layers are going to incline or go upwards because as they move forward. So you can see here they were going this way. On this rock they were going this way. So you can look at the inclination there and see. Porosity. So porosity is the percentage of open space between grains in a rock. An example, loose sand can have a porosity of up to 40%, and some of those open spaces are maintained during the formation of sandstone. The incomplete cementation of mineral grains can result in porosities as high as 30% in completely formed sandstone. So in other words, during that cementation process, what we talked about with the Rice Krispie treat, if you don't have enough marshmallow, you're going to end up with a porous surface. And when the pore spaces are connected to one another, fluids can actually move freely through the sandstone, making it very valuable as a source of an underground reservoir of oil or natural gas or groundwater. So sandstone can be very valuable in that way. So classic sedimentary rock that is fine grain, siltstone and mudstone, good example. They consist of mud and silt. Siltstone, mostly silt-sized grains, and shale, mostly silt and clay-sized particles. They're fine grain, they have low porosity, so they form barriers that hinder the movement of groundwater and soil, so they act more as barriers. Now, chemical sedimentary rocks. So we talked about chemical rocks. During weathering and erosion, these minerals are dissolved and carried into lakes or ocean. As water evaporates, the concentration of dissolved minerals is higher. And as dissolved minerals in the body of water reach saturation, this is another way, the crystal grains can precipitate out of the solution and settle to the bottom. So you can either have a whole lot of minerals that go into the water and create more minerals than water, a greater mineral to water ratio, or you can have water evaporating that creates a greater mineral to water ratio. Either way, those minerals are going to come together and precipitate out of that solution, and they're going to settle at the very bottom. And these layers of chemical sedimentary rocks that forms are known as evaporites. Okay. Organic sedimentary rock, we talked about that for a minute. So forms from the remains of once living things. Most abundant is limestone, which is composed of calcite. Limestone forms when the calcium carbonate in the shells of once living things precipitates out of water and crystallizes between grains of carbonate sediment, forming limestone. So we have this existing carbonate sediment, and we're going to have the carbonate, the calcium carbonate in the shells precipitating, and they're going to form between those grains, and it's all going to come together and make limestone. A lot of times in sedimentary rocks, we can see fossils. We can see the preserved remains or impressions of other evidence of past life, particularly in our organic rocks such as limestone. So sedimentary rocks are typically where we're going to see fossils preserved. Another example of organic sedimentary rock is coal. It forms from the remains of plant material as thick layers of vegetation in swamps and coastal areas accumulate over time. So what happens, these layers get buried and they get compressed and they become lithified and they slowly form coal. It's composed almost entirely of carbon, and as we know, it can be burned for fuel. It's a very excellent source of fuel. Okay, so metamorphic rock, our final type of rock. So what is metamorphic rock? So when high pressure and temperatures combine to alter the mineral or chemical composition or the texture without melting the rock, that's metamorphic. So pressure and temperature is going to alter the mineral or chemical composition. It's not going to melt. We're just going to have these temperatures and pressures that are going to not going to melt it completely, but going to heat it up, going to give it a little more pressure, going to kind of move those atoms and molecules around. So types of metamorphism. Regional, mapped predictions of metamorphic rocks based on temperatures at different locations. So we can kind of know what type of metamorphic rocks we can find in certain locations. Contact, when rocks change because of coming in contact with intrusive igneous rocks. So intrusive igneous rock is going to be pretty hot, and it's going to be there underneath the Earth's surface. And so when they come in contact, some of those elements come together. Hydrothermal, when contact with very hot water changes the rock composition. So you can have water coming in, and that very hot water can come in and combine with some of those elements, and that can make a difference. So that's your metamorphic rock. So as you can see, it's the rock cycle. It looks like a complex system, but actually it's pretty easy to explain. And so this is an overall view of the rock cycle. And now I have some critical thinking questions for you. So compare and contrast magma and lava. What two types of igneous rock are formed as each cools? So you should be able to go back and look at the definitions of magma and lava, and also determine what types of rocks are formed. What are factors that affect the formation of magma? So once again, in this presentation and in your notes, we talked about 4 different factors, so you can go back and look at those. Compare and contrast graded bedding and cross bedding. So you remember in sedimentary rock, we talked about 2 different types of bedding that you can find. So compare them and contrast them. And then finally, describe 3 types of metamorphism. So there are 3 types. And if you go back and look in your notes, you can see those as well. So answer those critical thinking questions. And in our next lesson, earthquakes, we'll go over the answers to these. And then we will go on and talk about earthquakes. Thank you for watching, and have a great